So, hi, I'm Daniel Newbrook. I'm from SoC Labs and the University of Southampton, and I'm going to go through our NanoSoC. So this is our microcontroller reference design. Firstly, I just want to go through, so I think as John highlighted on our website, on our platform, we have information on the different stages of the design flow. We start this off at a very sort of generic, high-level stage, and then introduce more of the specifics for different softwares, as well for different of our SoC reference designs. And I think as we build it up, we'll add in more for projects as well. Like I say, so most of this at the moment is around the SoC design. On our website, I think something key to highlight is we really want to encourage the community to add their knowledge. I mean, as much as we're doing it, we'd love to have some more from experts in the field as well. So I'm going to take us through basically NanoSoC through the flow here, starting off at architectural design. As we've been introduced, the ARM Academic Access has got a significant amount of IP available there, and one of these is the Cortex M0 system design kit. So in this, you have a basic M0 system with AHB and APB components that you can use, simulation framework, documentation, validation. It's a really nice small system. What we've tried to do with it is just take it a little bit further. So one of the issues with this, with the CMSDK, is it has a single manager, multiple subordinate bus system. So we've tried to overcome some of the bottlenecks in the bus architecture. We've taken it from a subsystem to then a full SoC implementation at the pad level. Added in DMA support for multiple DMAs, two instantiations, or up to two instantiations and different DMAs, as well as adding in our SoC debug controller, which, there we go, just there. Everything that we do is in the public domain, so it's all on Git. If you want to have a look at it, it's all on our website. So please do take a look. And I think then the most important addition to this is the added expansion region. So this is a memory map space where researchers can add in their IP. So going into a little bit more detail about this architecture, the DMA support that we've added, we've got the DMA 230 from ARM, which is a very, very small area, little efficient DMA. We can have one or two or none of these in the design. At SoC Labs, we've sort of enhanced the design a little bit at the top level to improve the bandwidth of this IP. And we've also added in the DMA 350, which is a much larger, much more complex DMA, so increased area. But it does provide support, so for two axis manager ports, which then can increase bandwidth. It also adds support for streaming. So I know a lot of the researchers we work with prefer to use an axis stream interface rather than a memory mapped interface. So this has added that support. Our SoC debug controller is a nice, simple ASCII debug protocol, as we're calling it. This, in theory, can be used without the M0 and just with that debug controller. It would be fairly slow, but it gives you a quite simple interface to the full memory map of the SoC. The main function that we use this for is debug, downloading code, particularly in the FPGA environment. So yeah, just a little bit more about this. So I think this is the kind of CMSDK image, and what we've done to take this to improve the bandwidth for the system over the bus is then expand this out into a full bus matrix. As with NanoSoC, what we've tried to do is make it configurable for people. So even for the bus architecture, you can make changes to this. I think quite recently. We've had a team where they wanted an extra DMA added in. We're happy to accommodate things like that. Off-chip communication is quite a big problem, particularly when you're trying to minimize costs, so you don't want to add in, costly IPs, keep it as simple as possible and as small as possible. What we've done is develop this, what we're calling XIO interface, effectively an external AXI stream with full handshaking. This then you can connect via a Raspberry Pi Pico chip to a USB to a host computer, and you can control, so it's standard in, standard out, as well as data in and data out. I know John's already touched on this, but I just want to go over a bit more detail in terms of the project structure and efficient reuse. We've laid out our repository in multiple sub-repositories, and the reason for this is then we can take some of those and reuse them across projects. I think particularly, there's obviously the technology side, but there's things like, so this SoC tools flow. What we've got in there is a lot of scripts, a lot of environmental setup that's can be generically applied to multiple projects. And then in terms of the project management, we've got on the website milestones you can set up to keep the date to. These all reflect back into the design flows of the sort of generic design flows. So onto the behavioral design. What we get from CMSDK, so there's the tarmac trace for the Cortex M0, what we've added in for the external interface, so you can preload the script. There's this command script at the start, which in your simulation environment will run to begin with. You can preload test vectors into the system. You can either do that over the interface as you would in in FPGA in silicon. You can also preload before the simulation starts. And what we also have is these AHB and APB sort of listener for the DMA and the accelerator port. What we try to do here is make the simulation environment give you access to as much information as you need, really, without necessarily having to go into the GUI, look at all the waveforms. For the FPGA deployment, we've targeted a few boards so far. So we've got the Kriya SOM boards, which is then for testing this external I/O interface. We've got the PMOD to a Raspberry Pi. You've obviously got the PINC interface with these boards and with the ZTU104, which allows nice, easy Python code scripting for the validation. We've also taken one of the ARM MPS3 boards for then a bare metal implementation. So really kind of trying to mimic in FPGA what we will have in silicon. The structure for this then, so we instantiate the full SoC just below the pad ring level into a socket, which has got clock, reset, communications. Then for downloading code, downloading vectors, we've either got the PINC environment over the AXI. For the ARM MPS3 board, we've got the UART comms, and all of these go into our ADP, our SoC debug controller. What we've done with these FPGA boards as well is made them into a virtual environment. So what that allows us to do then is continuous integration and continuous deployment, so that we can validate our design as we go, as we commit new changes to the Git. We've tried to make this, cover the full design as much as we can, and it goes through all of the stages. So the software compilation, behavioral simulation, FPGA builds, and deployment onto the virtualized FPGA platform. So logical design. So the first part of this, I say first, it's kind of, you can mix it in a bit, is the technology selection. What we have access to in Europe, obviously, we have Europractice, which is nice. So that Europractice gives us access to a lot of different technology nodes. ARM as well, they have their physical IP for a significant number of technology nodes from 250 nanometers all the way down to 5. What we've picked as a nice price point, and good kind of availability on shuttles is the TSMC 65 nanometer so far. Like John said before, so we're working on 28 nanometer soon and 16 nanometer hopefully by November. So sort of the synthesis side, starting into the back-end flow, what we've taken is through this, this full design flow. I'm only going to cover this very briefly, so there's a lot more information on the website. But what we've managed to do for the synthesis and for the back end is close, so 240 megahertz for this small microcontroller system, which I think is quite good. And as John was saying before, one of the big points in academia is power measurement. What we've done there is then split NanoSoC into 2 power domains. So we've got a sort of top level, which is it's got the M0, it's got the DMAs, it's got the memories, and then an accelerator power domain, which is just purely the accelerator. What we've done with that so far is taken it to the pin level. So there's a accelerator power supply separate, so that we can measure externally. What we're going to do in the future is take this so that you can have internal power monitoring for more of the tasks involved in at runtime. So particularly things like data movement. We would like to separate it out so that the DMA and maybe the SRAMs are on their own power domain, and you can measure quite high resolution, hopefully, how much energy you spent moving data, how much energy you spent pre-processing data or post-processing, and then obviously in your accelerator, in your hardware itself. So the result of this, the synthesized design at least, is less than 0.5 millimeter squared core. Most of this is macros, most of this is SRAM. The actual logic itself is quite small. And in terms of the estimated power consumption, 65 milliwatts. In reality, so we've obviously done the tape out now, it uses more like 5 or 6. And then the last, the sort of last of the back-end flow is place and route. What we've got developed so far is flows for Cadence, Genus, and Innovus. We're working on the Synopsys flows as well. We ideally want to be able to support as many of the tools as we can, so that if you have your own particular preference, we can help with that too. In terms of the back-end sort of simulations, so gate-level sims, post-root sims, the test bench that we developed for the front end is almost exactly the same as the back end. So you don't have to preload any of the RAMs. You can load it all over the external interfaces, which then gives you more confidence that the silicon you get back, you'll actually be able to sort of talk to it. The fundamental floor plan for this then is a 1 by 1.5 millimeter area. This is about the smallest we can make it. We have played about with smaller SRAM sizes and things like that, but I think for a sort of useful SoC, this is about as small as we can get. And this, signed off nicely at this size. We have found that, at least the typical timing, there's a little bit extra wiggle room on the setup slack, so we could possibly get this to run faster. It's not something we've really investigated yet. And I've already really covered this, but same simulation environment for the gate level as well as the front end. So what we've done so far is last year taped out 2 custom accelerators in NanoSoC. These were from the 2023-24 competition, both in our sort of education track. So we split the competitions into education and research, and on the education track, it's much more about the learning journey. So we had a master's student doing AI, so a systolic array for AI, and a PhD student at Southampton working on a sort of a KNN, or efficient KNN algorithm in hardware. And then finally, once we got silicon back, so the test boards, we tried to keep this very simple. In the way that we've designed this is so that you can use these Raspberry Pi 2040 chips. The reason we've done this is to take a lot of the area away from NanoSoC. So for things like SD cards, screens, other peripheral management, so like I2C, we've taken that area basically out of NanoSoC to keep it small as possible and then offloaded it onto these RP2040s. Good. Okay, I'm going to pass over now then to Rami. So he's one of our contestants from, he started last year. He's got a project around arrhythmia detection in NanoSoC. So pass over to you.
Good morning, everyone. So my name is Rami Hariri. I'm a postgraduate researcher at Anglia Ruskin University in Cambridge. And today I'm going to talk about my project, which is the A-Cube, or Arrhythmia Analysis Accelerator, building an atrial fibrillation detection on the edge. My project is a collaboration between my university, Anglia Ruskin University, and ARM. And at the beginning of my journey, at the beginning of my PhD journey, I joined the SoC Lab community, which I found extremely valuable in terms of support I receive, technical support, and any other issues I faced during my project. Okay, so first I'll just give you a small introduction about what my project is. So let's just start by understanding arrhythmia. So arrhythmia, as we know, is a heart condition characterized by irregular heartbeat, where the heart may beat too fast, a condition called tachycardia, or too slow, a condition called bradycardia, or simply in an irregular pattern. So its prevalence, arrhythmia is a common cardiovascular disorder affecting millions of people worldwide. To give you an example, in the US alone, there is currently 40 million people living with diagnosed arrhythmia. Types of arrhythmia. Arrhythmia can be atrial if it's generated in the atria of the heart, or ventricular if it's generated in the ventricle of the heart. And they are classified based on their speed and regularities. Some types of arrhythmia may cause sudden death. As an example, in the United Kingdom, in the UK, there was around 100,000 related deaths related to arrhythmia. Some every year, every single year. Now, some of these deaths could be avoided if the arrhythmia has been detected earlier. So causes and symptoms, various causes contribute to arrhythmia, and these include excessive alcohol or caffeine consumption, stress disorder, heart disease, or high blood pressure. Symptoms, it may include palpitation, where the patient is aware that the heart is beating too fast or too slow, dizziness, chest disorder, fatigue, fainting. However, some arrhythmia may be present without any noticeable symptoms. Diagnosis and treatment. Arrhythmia is diagnosed by measuring the electrical activity of the heart, known as ECG. It can also be diagnosed by measuring the sound of the heart, the echocardiogram, or by electrophysiological studies. Treatments of arrhythmia may involve lifestyle changes or prescribed medication, or even medical procedures such as catheter ablations. In ablation, the surgeon inserts a catheter inside the heart and they shock the region of the heart where the suspected arrhythmia may be originated. By shocking this region of the heart, the arrhythmia may be cured. Importance of monitoring. So regular monitoring is crucial for early detection and effective management of arrhythmia, preventing potential complications. But monitoring, doesn't need to be done occasionally. Monitoring needs to be done constantly. We require 24/7 monitoring. Therefore, we require a low-power microcontroller with processing extension to prolong the measurement time by reducing the amount of energy used to be able to do analysis and detect arrhythmia on the edge. Therefore, and that's where our arrhythmia analysis accelerator comes in handy. Here we have the NanoSoC architecture that Daniels explained earlier, and attached to it we have our AQ, the Arrhythmia Analysis Accelerator. So we propose a pre-designed, pre-verified interconnect to meet the performance, power, area, cost constraint of patch sensors for physiological signal capturing. So we propose a case study where atrial fibrillation detection using deep learning. Why we're using atrial fibrillation is because it increases the stroke risk by 5-fold. If the fibrillation is originated in the heart, there is a chance that a blood clot will form in the heart. If this blood clot is pumped into the brain, the patient will get ischemic stroke. If this blood clot is pumped into the heart, the patient will get ischemic heart attack. So the atrial fibrillation, as we explained, it increases the stroke risk by 5-fold, and it has accurate diagnosis for crucial, and use deep learning for atrial fibrillation beat detection. The data was divided into a 100-beat window. Each beat represents the time from one heartbeat to the next. We also refer to it as RR interval. And the database used is the MIDBI atrial fibrillation database. So the expected performance were 98.51% accuracy across cross-validation and 99.77% across blindfold validation. It's a robust system for long-term heart monitoring, and it was first to use the deep learning for atrial fibrillation detection. Here's just an image that shows the ECG signal where we have the normal heart rate and where we have atrial fibrillation. And we can see the signal has slightly changed, and we have a closer gaps. So the technology we'll be using is the NanoSoC and the HLS4ML. The HLS4ML translate the deep learning model from the Python environment into the hardware models. So here's the HLS4ML design flow. We choose an AI model. We then use HLS4ML to generate a quantized model. Quantization is needed to transfer from floating point precision into fractional fixed point precision. This quantized model is then translated into a HDL model in Verilog. Xilinx is then used to implement the HDL model and generate the bit stream needed for the accelerator. So the deep learning, we first chose the LSTM AI model, and how that it works, we chose 100 heartbeat, represented here by a blue dot. We took a group of 100 heartbeats. We fed them into LSTM bidirectional LSTM layer, followed by a max pooling layer, and then a fully connected layer where the signal will generate a bidirectional signal 0 or 1. 0 indicating no atrial fibrillation, 1 indicating the presence of atrial fibrillation. So here we have the communication between the ARM microprocessor, the Cortex M0, and the A cube. The communication between the Cortex M0 and the A cube is done via the double buffering methods, also known as the swing method. We have 40 RR interval, and then we have a 20 register, so 2 RR interval in every register. We start by by processing the first group of 40 RR interval, and then while these 40 RR interval are processing, we start filling the second 40 RR interval. So the processing start by writing to the control register. So while the low buffer is processing, we start filling the high buffer. Once the AF detection processing is complete, it issues an interrupt. We read the status register to see what causes the interrupt, and then we write to the control register to cancel the interrupt, and then we read the 16-bit register from the core. And then we repeat the same process again for the high buffer. So here we have the AF detection accuracy matrix for the LSTM model that we chose. We found out that a matrix of 40 RR interval and 20 LSTM unit was sufficient to achieve an accuracy of 99.02%. And then here we have the maximum value in each row of the data frame around the number of bits. And then for the 16 bits, the accuracy starts to saturate. That's why we chose 16 bits. Here an example of the LSTM memory cell. In the LSTM memory cell, we have 3 sigmoid functions and 2 tan functions, which is when we try to implement them, it requires a lot of lookup table resources, as we'll see in the following slides, which was too big to be implemented in ASIC. So here we have the main FIFO for the LSTM model, and it has 16 register wide and 40 stage deep, and it has 20 layer in layer 3, 38 register in layer 4, and 3 layers in layer 13 and 14. So the synthesis to gate level is done through Synopsys GTEC, generic technology library. It has 640 data register array plus, 7-bit pointer, empty flag, and full flag, and 649 D-type register for output and output invert. The verification test bench is instantiate original Xilinx FIFO as a golden reference. We have instantiate Verilog gate level, identical input, separate output, 48 push counter, 48 pop-up pattern, push and pop 48 entries, and no functional diversion. When we try to implement the lookup tables for the tan functions and the sigmoid functions of the LSTM unit, we discovered that it will require a lot of resources. For example, for the sigmoid function, it will require 60 ports, and for the tan table, it will require 18 port access. So the implementation option, no microarchitecture change. We give an hexadecimal data file, machine translation to address case statement, ROM, RTL analysis, machine translation to binary text file, and both rely on generated statement instantiation scripting. The implementation of the TANH and the sigmoid, as we said, it requires lots of resources. So for the TANH, it requires around 40K gates, and for the sigmoid, around 100K gate. And we use inverters, NAND gate, NOR gate, OR gate, and the multiplexer XO2. So the behavioral preload RAM took around 1.5 hours to complete. The case statement behavioral lookup tables around 1.75 hours. And the gate level RTL netlist around 59 hours to process. So here, then we chose the QDense model because we figure out the LSTM required lots of resources. So choose the QDense model with a sigmoid activation function. So here is the analysis of the accelerator design. And we got 2.5 by 2 millimeter area and 77% utilization ratio. So the area was still a little bit bigger than what we expecting. We aiming for 2 by 2 millimeter. So then we wanted to do further analysis. That's, we call it RC1, Release Candidate 1, the QDense model with a sigmoid function. And the number of ports required around 59,000, the number of nets around 821,000, and number of cells around 553,000. Then this is our release candidate 2. We changed the sigmoid function and we used a ReLU function. So the QDense model 640 is 640 reuse factor. That's why we call it 640 with ReLU activation functions. And the analysis was 1.5 by 1.5 millimeter. So it's possible to implement in a chip. And it has 76% congestion. And here are the RTL analysis for the release candidate 2. And then we tested the QDense model on 50,000 vectors with a best threshold 3.52. The accuracy was 93.29% and sensitivity 95.99% and specificity 91.06%. Here's a comparison table of the resources between our first model, the LSTM, and the QDense model with 640 reuse factor and the ReLU activation function. So we could see a reduction in resource utilization, in some cases around 75 to 80% reduction in resources. Our next step is we aim in with the help of SoC Lab for a tape out. And the technology we are targeting is the TSMC technology, 65 nanometer low power mixed signal radio frequency chip. My project milestone so far, I'm heading into the end of my second year and then starting my third year next month. So we implemented and tested the NanoSoC encryption example in FPGA at the beginning. Then we implemented the AF detection core. We analyzed the model performance based on different signal length and algorithm. We analyzed the model performance based on different quantization level. We selected a suitable candidate, and then we simulate the RTL for the selected AF detection core. We implemented an AHB bus interface for the selected AF detection core, and then we integrated the NanoSoC and the selected AF detection core as well. We simulated the integration result, and our next step is to produce the ASIC implementation and then do final verification and power measurements as well. Thank you very much for today. I'm happy to take any questions. Thank you. Okay.
So I'm going to quickly take us through now, so the NanoSoC sort of analog subsystem and analog and mixed signal integration. So you can only get so far with digital alone. So our SoCs can be improved or extended with analog and mixed signal IP. The way that we've done this in NanoSoC is to taken the our peripheral region, which is the APP subsystem, to include an analog subsystem. And then we've split this in so there's a dedicated analog and mixed signal bus and the sort of digital side as well. Yeah, sorry. So, as you can see, the split down here. In terms of what components you can add here, it's almost your imagination's the limit. In terms of, we've got some mixed signal components which really are more suited towards the sort of digital almost support. So there's things like the PLL, voltage regulators, power monitors, as well as like SLM, so silicon lifetime monitoring for voltage, temperature, and process. And then more in the sort of analog mixed signal domain, your ADCs, your DACs, as well as sensor conditioning or signal conditioning for amplification, filtering, anything else you can think of. So in terms of then physical integration, we've had to bring obviously analog pins up through our hierarchy all the way to the pad level, including then changing the analog power structure. I mean, in terms of the way that we do this, you can separate your digital and analog domain, or you can kind of try to combine them as well. And this is where care has to be taken. Obviously, in this, we're doing this as a digital on top design flow, so all of the analog IP is going to be treated as macros. Taking a example here, so we've got this ADC integration in NanoSoC from our last year's, this year, the competition that's coming towards an end, where we wanted to really focus on real-world signals, real-world test cases. So in terms of sort of why you want to do this on chip, it adds more flexibility in terms of what you want to do. So you can add in things like your signal preconditioning, particularly if your area of interest is analog. In terms of data rates, data transfer rates, this can be preferable as well. But obviously, designing these high-speed ADCs is a challenge in itself. Off-chip then, if you're more focused on the digital processing, if it's relatively low frequency, low bandwidth, and then, it simplifies things a bit because then you don't need to do the analog design. You can just put it all off-chip. Just to then, go into a bit more detail, this is then the added region in the address space. So it's all, again, fully memory mapped. This can be seen by all of the managers on the bus, including then the off-chip interface for the SoC debug controller. The way that we started with this was from the digital side. So we used the Verilog AMS as a simplified model for the ADC. We see a very a very kind of common successive approximation of our analog signal. Then, so taking this as a fully integrated sort of subsystem with this model, using the APP bus interface to control what's going on inside the ADC. Converting this, reading this back. So, you can see from the simulation environment, this is the input, so the low frequency sine wave. When we reconstruct it back from the data over the APP, we see what we'd expect. So that's nice. Taking this then to actually designing the ADC, schematics and layout capture. We've taken a very simple design, so just a successive approximation register, ADC, just because it's reasonable speed, reasonable accuracy, quite low complexity, at least conceptually. The specifications that we've targeted here, so it's 8-bit, 100 kilohertz. We wanted to kind of at least include audio frequency ranges. We've kept it at quite low voltage as well, trying to keep it low power, and as well, keep it fairly accurate. We've not put numbers here. We just kind of wanted to say low non-linearity. In terms of then the blocks and the design flow, so we've separated this out into the full ADC, the internal DAC. Here we've chosen R2R just because, again, conceptually it's quite a simple design. Track and hold, comparator, and then the approximation register. In this, then there's things that are reused. So the analog switch is reused. We've got gate reuse, op amp as well, I believe. So in terms of this, this is the block specification. You take each of these blocks to schematic, verify them, do the layout, verify again. Go round and round as many times as we need to get it working. I'm not going to go into detail into all of the blocks, but this is the top level simulation. Again, is a kind of simple design for these SAR ADCs. They assert bits from most significant bit to least significant bit and compare against what the DAC will output to what the actual track and hold has held onto as a value. But we see here nicely that it's, again, following the sine wave. We actually found with this that we can push this a bit harder in terms of frequency, so this can go up to about 1 million samples per second. Power consumption in this design is really dominated by the DAC. The R2R is not the most efficient design. It's just kind of the easiest that we could pick up, and that's definitely kind of point for future work. And we do see a bit of scaling with the power with frequency as well. Although to be honest, that the DAC that's about as low as it gets for that because of the static power consumption. We see with this, error-wise, it's quite good. A nice sort of linear following. A bit of an issue around the middle of the graph here, so from 0.6 to 0.8 roughly. So it seems to be where the comparators moves from sort of PMOS to NMOS driving. So it's an issue I think we've identified. I just think we need to fix it. And now the point to reflect on is have we actually met the specs that we put out to begin with? So we've got the 8-bit resolution, sampling rate's good, conversion's good. This is not so good, but it's good enough for now, and we've identified problems. We just need to do the work, and we've kept it quite low power. In terms of the digital interface, just to go over quickly, so this is a APB subsystem. There is clock divider control, enable, disable. We're trying to make it so that we can completely turn this thing off to keep the power as low as possible, and as well with interfacing and status. So I'm going to quickly now move on. I think we're in the interest of time. So Eric here is now going to start talking. So Eric's from the University of Sydney. He's been working with us for last year, his team, and on their project for sensing for precision agriculture. I'll pass along to you. Yeah.
So thank you very much, Daniel. Thank you very much, everyone, to be here with us. So yeah, I'm coming from Australia, Sydney. I arrived this Sunday, so it was a kind of long flight. So thank you very much for being here with us and take the time to be with us. So yeah, I'm representing the team. I'm part of the analog team. Okay, mainly how we start with this. Most of our team members, we are always dreaming about design a chip and analog subsystems. But usually in the traditional coursework of the universities, we don't have this kind of opportunities, or we don't have the chance to develop a really big project, usually our pre-made projects. So we are always really passionate about this kind of design. And right now, like SoC Labs gave us the opportunity to develop a whole project that is not attached to a traditional coursework. It's not attached to a traditional way to work. That is more real, more into the real world. So let me introduce our team. We are 9 team members. for undergrad and for postgrads, including myself. We have a bit of background in barrel of FPGAs and computer architecture. We receive support of the university from the School of Electrical and Computer Engineering, and also SoC labs we have. So basically, the main purpose of the team, it was create a whole system, digital and analog. So we are divided into teams. The analog front end, that is, we are 4 members, and the SoC design or digital team, 5 members. Okay, we created the main objective of this project was create a mixed signal SoC contain both parts, analog and front and digital components. It was a really great opportunity to learn multiple skills that are not commonly learned in a traditional coursework and develop more skills that are valuable in long term, excluding this project that it was valuable. So after multiple sessions of brainstorm, we decided to create a precision agriculture on a system of chips. The main objective of this is save water, one of the most valuable resources that we have. So we are looking to do more efficient how is the agriculture and support the multiple stakeholders, the government, the local communities that will need in long term that water, and the farmers that is a cost that is really expensive to in the long term. Is a really expensive cost. The advantage of this project, we are aiming to have energy efficiency, low effective QNH scale up, compact form factor, efficient water management. That one is our main focus right now, and improve the agricultural productivity. So before this project, no one of us have any experience designing SoC. So this is how SoC Labs gave us a lot of support. And how? Okay, mainly they gave us support to access to the ARM M0 Cortex, that it was a great starting point. Also multiple IPs that allow us to accelerate our development of the project, that it was a great starting point. Overall, also we have to adapt it to our project, but this one accelerate a lot, and mainly mentoring that when we're struggling with any kind of these problems that we are not sure how to proceed, that we don't find any specific solution, SoC Labs support us with the forums and with the mentoring of John and Daniel sometimes. So we have 2 main goals: learn SoC design and flow. This one is on charge, the digital team, and design an analog front end. This is on charge, the analog team. So okay, starting with the first goal, learn SoC design and flow. As I mentioned before, the documents provided by SoC Labs, it was the ARM Cortex M0. This one was a great starting point to learn how to design everything. And this is the design flow. We have our IPs, our storage, and our bus interface logic, or FIFO buffer, the multiple. We create a IP and APB wrapped of sensing peripherals. These ones are already done, implemented in our project. And our MVP, digital peripheral integration, and tested. So our sensing peripheral, introducing our SoC peripheral design, collected, this one is the diagram, is collect data independently of the processor. This one is to assure power efficiency. So if the processor is not, we are sure that we are collecting enough data for 24 hours until we turn off the processor using the ADC that Daniel previously said, that we adapt in our project. So the timestamp data with 1 second of the sampling event, collect up with 24 hours worth of data in temporarily buffer 15 samples per hour. And we start with the ADC SAR that Daniel provided us during the development of this project. It was really useful, and this helped us a lot in the development. It's an 8-bit resolution, 100 kilohertz sampling, and 1 to 0.2 volts of coverage range. The sampling rate is really almost perfect. We are going to go further there in the introduction of the analog part. But also, as control unit, we implement a finished state machine that combines the FIFO and the ADC and the multiplexer. This one worked with the RTC that it was provided by SoC Labs and the processor triggers. This is the diagram of final state machine. It's kind of simple, but there is the idea. And this is the addresses or RPP interface. We're planning to implement more for debugging and the scale up in the future, but these ones are already delivered, tested. And functional simulation. Basically, we create a Verilog test bench and NanoSoC test frameworks. So here is more visible, or empty FIFO, filling and emptying the FIFO. So, okay, the first one is the trigger ADC to sample. Secondly, is the mock ADC data is pushed into FIFO. The third part is the FIFO is full. Okay, in this moment, the processor reads proper FIFO values until it's empty, and the FIFO is going to be again empty. Okay, going through the second goal. This one is the analog part, the analog front end. This is a little diagram of our analog front end. Design an ASIC implementation for the TDR master sensor. And we are working right now in a full simulation of the TDR in Cadence that we are going to start with that later. Okay, at the beginning of this project, we start with multiple sensors. Temperature sensor, soil pH, compact salinity, many sensors that are used in agriculture. But we decide to focus only on one, that is the TDR sensor, time domain reflectometry. Why? In the United States, it seems like it's really common to be used, this one. So treat the soil as a transmission line. Are multiple alternatives, the VDR, capacity basis sensor, dielectric permeability sensors. But right now, this one is really expensive in the market. So we want to reduce a bit the expenses of how expensive it is. And this one calculates the dielectric permeability from the time it takes from the electromagnetic waves to travel through the probe and return. These ones are some of the specs that we are looking at the final of this project. The commercial ones that are in the market right now, they can perceive precisely from really dry sand that is no water, 0 water on that, and really to literally all full water, 100% humidity. So it's really accurate, those ones. Unfortunately, we are not aiming for that really big range. We're focusing in a really small range, more real world, to say it in one way. We don't have the expertise. We receive some mentoring. We receive some mentoring of one person in industry that is helping us. But even that, he is not almighty. So we don't have too much time. This is our analog front end. We basically are the three more important parts: the pulse generator, the timing, that we implement 2 delays that we are going to talk a bit more about that later, and the sample receiver. We are going to go through all of these modules later. Okay, one of the most important concepts here is the time sampling. We're using equivalent time sampling. We're using this one we are using the ADC of Daniel, that we are using a frequency of 120 kilohertz of sampling. However, what is how is sample in the real world is 1 gigahertz, 2 gigahertz. So in this way, we are collecting way more data with the ADC. And these ones are the equivalent time sampling. That is more, this one is just a representation of the pulse generator, the timing and sample receiver. So as we can see here, is the pulse generator and the sample receiver, and this one is as only one cycle. If we zoom out, we can see a couple of cycles. We're collecting like we're collecting 15 samples, but of the final, we are only reconstructing 2 samples. That is the way that we are collecting more data with this low spec ADC, because we want to consume as less power as is possible. So this one is one of the models that we are taking as reference, the CS630. And this is like the cadence model simulate reflection. That this one we got access through from their academic program, so it was really useful. So we have here the pulse generator with a 50 with a standard 50 ohms resistor, the coaxial cable of 1 meter, and the probe of 15 centimeters. So this one is the pulse wave generator, 1 meter, and the probe model. This one is the simulation with the generated pulse and the reflection. We have here the first reflection, the negative part, and after that are just like the other reflections that are generated by the open circuit here. And the starting waves altitude over time, yeah. Secondly, we have the delay. This one is to compensate the problem, the delay that the coaxial cable is going to have during the time. We are going to have intervals of reflections of 20 picoseconds, but the coaxial cable have a delay of 9 nanoseconds. So for this, we have 2 different delays to compensate that delay of the coaxial cable. The delay 1 that is between the PLL and the DLL, and the delay 2 that is between the DLL and the sample head. And our pulse generator define performance specification by set of typical soil properties. This one is just like performance requirement dependent of the interplay between the soil and the probe properties and the pulse shape. This is visible here. And after that, we have the pulse generator, the standard 50 ohms impedance of the output of the pulse generator. We're aiming for have a bandwidth of 400 megahertz to 100 gigahertz. Some products in the market go a bit further than 1 gigahertz, but it's not that common. But we are aiming for that. But for that is the sampling that we were talking about, because we are going only collecting 120 kilohertz. And the voltage used. The maximum is 1-2 volts. Most of the products use a bit more than 1 volt, with some exceptions. And the next steps in the pulse generator is the simulation with typical values for soil. That we are working on that with one mentor that we got, and select appropriate design prototyping to meet performance specifications. And this is the sample head, 100 megahertz to 1 gigahertz bandwidth range. We are using a Scottish diode based sampling circuit. This one is helping us a lot with the precision. We are looking to precise acquisition of the short duration reflections and handle reflection signals with a rise time of 300 picoseconds. Okay, this one is one of the outcomes that we as team, we didn't expect directly. That is the project management. That is something that as engineers, we don't consider it that much overall. If you are working in industry, usually you have a project manager, but you are not the project manager. But we have to set up objectives. That is like the main thing of a project, have a specific goal, the project management plan or milestones, the organization, that is our team structure, digital analog team, and the work breakdown structure. These ones are our current milestones. Right now, the analog team, we are in the milestone number 5, and the digital team, they are a bit further in the milestone number 6. And SoC support us mainly in the milestone number 2, 3, and 5. However, they always support us all the other milestones. But these one are the main contributions of SoC Labs. And we have future direction, then analog front-end implementation, the simulation of prototype and prototyping, the physical implementation, and the power and area optimization. So that is all. Any question? Yeah.